So we're having a talk on RAG using various tools with or without OpenAI by Christy Bergman, who you will meet in a minute. This is being drawn here at Hacker Dojo by San Francisco Bay Area chapter of the Association for Computing and People, ACM. We were founded in the Bay Area in 1957, and we try to promote knowledge of our computing, create communities for networking and hiring. Our membership to our chapter is $20, annual membership. You don't have to join, but it certainly helps us. We have some upcoming talks that you will find on our meetup page, which you can see, search for SF Bay ACM. And we have a whole bunch of talks, hundreds of talks on our YouTube channel. We try to have 2 monthly meetings, one on general computing, generally on the 3rd Wednesday of the month, and one on data science and AI and all that sort of thing on the 4th Monday. And during the meetings, we like to promote interpersonal networking, job hiring, announcements, and that kind of thing. And we sometimes have joint meetings with other societies. We are a volunteer-run organization, and we certainly could use volunteer help with things. You're here at Hacker Dojo, which is also a volunteer-run organization for the most part, and a nonprofit. And so consider coming back, learning more about it, and possibly joining. So Christy Bergman is speaking tonight. You've heard good data matters in machine learning, but does it matter for generative AI applications? Corporate data often differs significantly from the general internet data used to train most foundation models. Join us here for a Python demo on building and customizing RAG, RAG stack using OSS Milvus, vector database, LangChain, Ragas, HuggingFace, and optional Zilliz, Cloud, and OpenAI, and learn best practice and advanced techniques to optimize generative AI workflows with your own data. And Christy has been 6+ years been building AI and machine learning systems with math and coding. And her mission is to help developers and customers use those tools with fewer heartaches than she has had in teaching herself. I think we can all appreciate that. To organize and search structured data, such as images and text, and using LLMs and multimodal apps. She enjoys learning new technology, and tools, and solving challenging problems with math and coding. As a developer advocate, she uses her skills in Python, HuggingFace, PyTorch, Spark, and several other technologies, and vector databases to create and share engaging and informative content, such as tutorials, demos, blogs. And she also manages the Bay Area Unstructured Data Meetup, where she organizes events and fosters a community of enthusiasts and experts in the field.
Okay, thank you. Well, I'm glad to be here. This is my first time here, so I didn't know what to expect. So happy to be here. It looks like I have.
Let me get my power cord there. Can you unplug that for me?
What happened here? So,
okay.
Welcome.
Thank you.
Everybody.
That's okay. I'll find that place.
So yeah, want to maybe later. I'll post usually people ask me, where's your code and where's your slide? So I'll be posting those out. Some of the obligatory slide, my company that I work at, it's called Zilliz. They are the company that maintains the open source database in Milvus. So that's where I work. They were founded in 2017. They're based in Redwood Shores. Yeah, so a lot of people have maybe heard of vector databases. Just this is a kind of a 1,000-foot view. There's a bunch of different open source vector databases out there now. You may have heard of them. So there's closed source and open source, and Python is an example of maybe closed source one that you've heard of. And then sometimes I demo both sides, but so we offer both the open source and then builds. And what's nice is you can write Python code and like for example, if you have the auto index or that you're using, open source it'll be HNSW and yeah, so yeah, if you have the same Python code, it'll be running HNSW by default in open source, and then in closed source, we have faster indexes that are proprietary. And so today, what I'm going to talk about is kind of what's a hallucination, what is RAG high level, a couple of challenges with RAG. It's still there's still a lot of things that need improvement with RAG, and I'll give a demo, and I'll also talk about how to evaluate a RAG pipeline. So you've probably seen these kind of things a whole bunch of times. For example, if I go into Bard and I ask, list 3 politicians born in New York, it's going to the first one it usually comes back with is Hillary Clinton. And then if you go to Wikipedia, you can see that Hillary Clinton was actually born in Chicago. So that's an example of a hallucination. And that's the problem with generative AI. And why do models hallucinate? Well, they hallucinate because these foundational models were trained on sequences of tokens. And so if you're trying to predict what's the next token in the phrase, the chicken walked across, it's probably the road. But because these foundational models are trained on all kinds of internet data, there could be random things that come out. And just a reminder of what we're going to be talking about here with the vector database. We're going to be using embeddings, and the embeddings come from the next to last layer of a deep learning model. And you can think of these embeddings like a big function, like an f of x. So they came from the transformer. The transformer has 2 parts, the encoder and the decoder. And at first, the first transformer paper, intention is all you need, had both parts. But since then, researchers have figured out that you can actually split this up into 2 parts, just the encoder part, and that's what are used for what we call embedding models. And these are the big f of x's, where you take your x is input, like unstructured data, like a paragraph of text or an image, and the x that comes out is a vector of weights. So yeah, that's the encoder part. The decoder part, we're probably more familiar with. That's the ChatGPT type of model that spits out decoded the next tokens, predicted tokens. And what is a vector? So that once you have f of x, your unstructured data, and turn it into numbers, then you can do nearest neighbor search in vector space. And these are called, you'll hear them sometimes referred to as dense vectors. And what we mean by that is the embedding output of the embedding models, vectors, which are floating point numbers, a lot of them. And the intuitive idea is that now you search nearest neighbors in this vector space, and the semantic search should be a result that the nearest meaning vectors in this vector space are close together. And just a high level review of what is RAG. So you've got your data, you do an offline, typically embedding model transform of all your data, and you store those resulting vectors into a vector database. When I first started, I thought, oh, okay, I'll just store them in memory. But it is kind of nice to have them stored in a vector database rather than worrying about having a Y or Python variable somewhere. And then you probably want to search that vector data. So this is the idea that you've got your own documents, and now you want to talk to your technical docs or medical docs or HR docs or something. So you ask it a question, you have to embed that question with the same embedding model that you used for the rest of your data, because in order for nearest neighbor search to work, it all has to be in the same vector space. So you embed your question, then you do nearest neighbor search, you get what's called a retrieval. The retrieval are the chunks of, or the nearest vectors, and those correspond to chunks of data from your corpus. And then you stuff those into your prompt. So now your prompt becomes a question plus the retrieved context. And then you feed that to the LLM. And that whole thing is called RAG, Retrieval Augmented Generation. And it's a pattern. And in theory, what should happen is that, especially if your data is very different from just general internet data, that the answers you get from a RAG pattern should be more reliable because they're based on your data versus general data. I realize this, I'm going to be talking for a long time, so I probably should pause every so often and see if there's questions. Okay, everything seems pretty standard.
Maybe you can take a poll of what people want.
Okay, who here knows what an LLM is? Great. Who here has heard of embeddings and encoders before? All right, so then you know the result of an embedding in an encoder is a vector, and then the vector stored in the vector database. And what we're going to do here is we're going to search the vector database for nearest neighbors to augment our prompt that we're going to feed the LLM. Okay, cool. Oh, question.
What the methods for only the embeddings or for the embedding and the effects exposure?
Good question. So the question was, does the vector store typically store just the vector or the vector plus the text? Usually best practice is just to store both of them because it doesn't take that much space, and it's a lot, granted it's redundancy, it's data redundancy, but it's easier to be able to look up chunks and what the corresponding text that went with those chunks if you just store them all together. Oh, thank you. All right. Good. Oh, one more.
So it's stored as a key value then?
Yeah, typically it's stored as a key value. So you've got a chunk ID, and then you've got the data that goes with that chunk ID. So the chunk, the vector, the text, and then you could have metadata as well. So like if you're thinking about movies, you might have like the movie reviews or the unstructured data. You're going to break up all those movie reviews into chunks. You've got the chunk ID, the movie review, and then the metadata, like the name of the movie, maybe the movie stars, the genre, and all movie poster, and all kinds of metadata. And that's all stored in the vector database typically. I'm going to start with that person back there who has his hand up.
Yeah, one thing I thought of with this, and I was wondering if it was a common problem, is that the vector database that we have, the proprietary data, shadows the content that sits inside the existing LLM. So for example, if I have my own version of the Constitution, and if there's interesting information about the Constitution inside the GenAI model, I don't see it because the RAG prompt basically shadows all the information that's there. Is that a problem with my implementation? A problem with LLMs?
Yeah, so I think it gets back to where things are going with LLMs in workflows. People are talking about agents. And so what you would do in that case is, like if you're asking a technical question about Milvus docs, then you should probably redirect that answer to your RAG workflow. But then if it's not about Milvus docs, it's about the US Constitution, or it's about questions about where did the name New York City come from, maybe that's better to go to Wikipedia or some other, path there.
I don't think that was your question, right? Your question was, it overshadows what's in the LLM.
Okay, so then you
Repeat the question.
oh, right. So the question was, what if somebody's just asking about known internet data and you have a RAG workflow, how can you make sure that you're getting that internet data and not your RAG workflow? And yeah, so I think this is where agentic RAG is going, is that you want to have a layer in there that can decide whether the intent of this question is general internet knowledge or the intent of this question is something specialized for your docs. All right, but good question. Yeah. Okay. Right there, I saw. Yeah.
What's the size?
Yeah, good question. So there's all kinds of different sizes. They typically vary from 256 to 1536, and it depends on the model. So yeah, they're much bigger than probably vector spaces that we thought about before, but still pretty small, pretty easy for yeah, modern computation to handle. Vector arithmetic. I saw a hand over here somewhere. Yeah.
Similar question. The dimensions on your vector, how that would to answer it?
Yeah. So that'll be a parameter of the model, embedding model. So the embedding model is going to say, what's its context length and what is its embedding dimension? So context length has to do with when it's trained, it takes like a window of tokens at a time and predicts the next token. That's the context length that it's trained on. And then the embedding dimension is the output from the next to last layer of weights in that model. So those are both fixed per model. Okay, question here?
Yes, so some of the newer ones, the context is pretty much unlimited or go very high.
Yes.
Does this take care of very large context in the sense of 1 million or maybe high 200K type?
Yeah, so the question is, you know, we've heard these days about long context windows. Now, keep in mind, when we're talking about RAG, we have two models here. We have the embedding model and we have the LLM. They both have context windows. Typically, the LLM has a lot larger context window. And this is the 8,000 or more, or, you know, that you've heard about that can be used. I'm going to talk about this a little bit later in terms of how to get the best results out of your RAG. But yeah, typically the embedding models have smaller context windows than the LLM, the generator. All right. Okay, cool. So I'm going to talk about just some different components of RAG. So the first thing is like, how do I get started choosing an embedding model? And there is a place called the MTEB leaderboard, which is a really great place to get started. So you go here, you go to the column that says retrieval, and you sort descending by the column that says retrieval. And this will give you, it's a good place to get started. It's going to list a bunch of models. Now, we don't live in a static world. And what's happened in the last year, or even less than that, like probably the last 6 months, is that because this training data, because the benchmark data is public, various companies have gone out there and they have overfit their embedding models to that training data so that they rank higher on the leaderboard. So for this reason, this is one thing that we do as a benefit, is that we will test these models and we'll only support the ones that are not overfit. It kind of becomes common knowledge, if you search for it, which of these models are overfit. So for example, right there, I see Voyage Light 2, Instruct, that's an overfit model. But they do have they have other Voyage models that are not overfit. And those are the production models that you need to use, not these leaderboard. But anyways, okay, this is something, it's still a good place to get started, to look, to just be aware of what kind of embedding models there are out there. And you'll see here, the model size, actually, I need to make this bigger. Oh, I guess I can't make it bigger. Okay. All right, so anyways, you see as the parameters, the model size, which is the embedding dimension that people were asking. So you'll see those numbers varying from, 4096 down to 768 here, for example. So when it comes to embedding models, another something that has come about very recently, is the fact that those embedding dimensions can actually be cut back quite a bit. I mentioned that I organized an event in San Francisco called Unstructured Data. So one of the speakers who came was Yuri Malkov, who's famous for inventing the HNSW index, which I'm going to talk about soon. He also was one of the people behind this thing called a Matryoshka representation learning, MRLs. And what he told us is that embedding models now are being, if they're trained with MRL, that you can actually get different size embeddings. And sometimes there's a smaller embedding with barely any loss of accuracy. So in the case of the most recent OpenAI embeddings, which were announced, I don't remember the date, but maybe 3 months ago, it's the new text embedding 3 series. There's a text embedding 3 small and a text embedding 3 large. And they both, interestingly, are offering 2 different embedding sizes, a small one, 512, and a larger one, 1536. And the scores of the 512 is exactly the same size, same as the score on the larger embedding 1536 size. And this is important to know because if you're going to get the same accuracy, you may as well use the smaller one because you're going to save on memory and be able to serve up chats faster with lower latency. So yeah, so this is something new and pretty interesting and pretty exciting. That now you can watch out for this, that bigger is not always better in terms of embedding length. Okay. The next thing you're going to do is, after you choose your embedding model, you need to think about what is your indexing. And in vector databases, indexing refers to a data structure. So probably a lot of people here took a computer science class where you had to go through data structures and learn about hash lists and linked lists and bubble sorts and binary trees, all kinds of different data structures that are meant for efficient search for different applications. So this is what's going on with an index. So the index is taking your data and organizing it into structures in such a way that it's going to be optimized for search. If you go to our docs, you're going to see probably an overwhelming number of index choices. So yeah, you need to kind of wade, like I'll just give you a high level. There's in-memory indexes, there's on-disk or on-disk indexes, and there's hardware optimized indexes. And within each, you've got different choices. If you're going to use in-memory, which unless your data is too huge to fit, most people can fit it in memory these days. So in that case, you're going to have like flat, which is a brute force index. You're going to have IVF flat, which is cluster, where you take clusters and you search nearest neighbors only in certain number of clusters, not all the clusters. And then HNSW is pretty much the default these days. And that guy who came and spoke to us, Yuri Malkov, is the inventor of this HNSW, which is pretty cool. But yeah, this is kind of the default vector index these days. It is HNSW. It's a graph structured a graph structure for the vectors to search them. I'm just gonna, yeah, floating point sparse. These are like in the old days, you probably remember TF-IDF or something where you had to map a whole corpus of all the words and assign a number per each word. Nowadays, it's gone away. The first step was to go away from that to like BM25 and SPLADE, where you have a machine learning model to predict a number for each word. And then nowadays there's these neural models for sparse vectors. And they're sparse because they're going to be really big, but mostly zeros. And only numbers where that word that you're looking for, it occurs in that text. And I see a hand raised. Yeah.
So, I thought third line there's a typo. The top layer is the sparsest. You miss the T.
Oh, okay. Thank you. Top layer. Oh, oops. I'm going to have to, I may as well fix it now. Okay. Okay, all right, let me, and then in addition, these indexes live on hardware, so there's hardware optimizations that need to happen. So just kind of an intuitive look at these things, added this slide so that you can see IVF flat, it's like a clustered approach to search where you have two hyperparameters to tune. One is number of nodes, how many clusters you're going to have, and then list, which is how many, so the number of nodes is during the index building, how many clusters you're going to have, and then list is during the search, how many of those, all of those nodes are you going to search? Like out of, if there's 4 here, am I going to search 2, for example? So that's the approximate part of approximate nearest neighbors. It works pretty well for fairly small data. If you got larger data, you might want to go to this HNSW. And in kind of intuitively, what happens here is that all the data has been taken and moved into kind of hierarchical graph structure, so that the top is the sparsest, and then the bottom is actually going to contain all of your vectors, where each vector is represented as a node. So if you search going top to bottom, so this makes it really fast. In that, like, let's say you come in here in the top layer, maybe there's only 2 choices or 1 choice to choose from. So you jump really fast to the next layer. And then maybe the next layer, there's only, 2 or 3 choices. So you choose the closest neighbor out of 2 or 3, and then you jump down. And you keep on repeating this pattern, and it just makes the search really fast to find. It's pretty much table stakes these days in vector databases. So you should expect to see this. Yeah.
One of the problems with embedding is that they capture semantic meaning. So
Yeah.
how does Milvus deal with exact search? Now, because you mentioned VM25, that's what I'm asking, like, does Milvus support exact search of keywords as well?
So the question is, how does Milvus support exact search? So if you're going to have a bunch of vectors, there's going to be one vector that is the closest to your search vector. And by exact, I mean finding that one vector that's the closest. Yeah.
My question was, for example, like, let's say my question is, give me details of contract number FH2750. No embedding can capture this FH2750 string. So how do you search for, like, how will you answer this question using that?
Okay, so the question was, I think you're asking about the difference between keywords and semantic search, right? Okay, I do have a slide for that. It's going to be coming, it's going to be hybrid search coming up. Okay. Yeah. And then another,
Give an appreciation for the index size, the number of documents, when it should be on memory versus when you should have them. Yes. And the size of the vocabulary. The GPT one is around 30,000. But if you have your own vocabulary, it's 500,000. Many of these things change.
Okay, let's see if I understand your question. So first question was like, when would you need to use a disk index versus in memory? And the second question was something about vocabulary.
So the GPT one and all these are basically trained on 20,000 words, right? The vocabulary which is built. There are other vocabularies like the medical and all where it is 500,000.
Oh, okay, yeah. So what do you?
Scale up is what my question.
Okay, maybe I'm just gonna like take a stab here at maybe a hidden question. So the first question is like, when do you need to use disk index? It really depends on the size of your compute. And most of these, especially if you're using the smaller OpenAI embeddings that are 256, for example, you could have a lot of like millions or billions of vectors possibly that will fit in your memory easily. So I've got a really wimpy laptop here. I've only got 16 gigabytes of RAM. I can fit 1 million vectors pretty easily on my laptop. So really, That's gonna vary depending on the size of your vector. How many vectors will exceed your RAM? The second question you were asking about vocabularies. So the vocabulary does not change the size or the memory requirements of your vectors, because what's going to happen is it's the embedding model that does the big F of X. And whether you're feeding it a medical document or you're feeding it, you know, the Constitution, I guess, the output size is going to be the same output size. Now, the thing is so that's the memory part. The thing is that output going to make sense? Probably not, because that not all embedding models are probably going to understand that, maybe that medical document. So this is where most of the time it does work. Most of the time you don't have to fiddle with the embedding models, but some people are like getting there. If you're worried about eking out like little bits more accuracy, then it does pay to what's called fine tuning, where like maybe you do like 5 iterations of training on custom data to get your embedding model more fine tuned. But the output is still going to be 256, for example. If you use as the base model the the embedding 3, for example. Does that help? No.
We can.
Okay.
There are a couple of questions online.
Oh.
Let me play them and you can decide whether it's appropriate to answer this point or not. So one question is, do not we start from layer 0, not layer 2?
Oh, can you repeat the question?
Shouldn't we start from layer 0 instead of layer 2? I'm not sure what he's referring to.
Oh, probably he meant the HNSW when I was saying you start at the top and go down. Maybe I don't know why. I'm sure it's called layer 0 at the top. Okay.
How does one define overfitting of an embedding? Is it a function of the context data alone? HuggingFace models that couldn't have overfit to the context in question compared. The question is not known. You do it.
Actually, that's the problem with the MTEB leaderboard, is the training data is known. So the questions and answers are public data. And so people have taken that public data and trained. So people who have a background in data science have learned about overfitting over the years. That's where you train a model, you have your data, you split it between train, valid, test, and then you train a model on the training data. If it's a good model, it should perform just as well on all 3 data sets, train, valid, test, or pretty close. If the model is overfit to the training data, what will happen quite often is that it'll look great in the training data. It will be like 99%, accuracy, but then there'll be like 1 data point or 2 data points that are different in your validation or your test data, and then your model is going to fail because it was overfit, meaning, hopefully that's clear. Maybe not. I don't know. Okay. Okay. I see one more question. I see that there's a question here about why does the embedding model for the question and for the question and your data have to be the same? It has to do with the fact that we're searching a vector space for nearest neighbors. And so if you need to have the same vector, you need to be searching in the same vector space between 2 vectors. The 2 vectors have to be in the same vector space for it to make sense to measure nearest neighbor. They need to have the same dimensions for one thing, and they also need to be having the same meanings, which can only come from having used the same model. Okay, one more.
Retrieval metrics. Wait.
Okay, something about would the Okay, I'm reading this question, but I'm not understanding. Do you mean the retrieval metrics like hit rate would be different? Maybe the question is like, if I used a different embedding model. Basically, it just doesn't make sense to have your one model for your question and a different model for all your data, because the definition of, you've got two different vector spaces and you're trying to measure a distance between two different vector spaces. It's just not gonna make sense. It has to be the same space that you're measuring in. Okay, I still see a question about what does overfitting mean? So in standard data science, when you learn data science, you see like a picture of like a bunch of dots, and then there's like a curve that goes through it, and that curve represents a function that represents all those dots. So like sometimes it'll be a line, and that line represents the model that's fit to those dots, and it's got a certain like error, there's gonna be errors between that line and all the dots. If you take the mean squared error of that line and all the dots, that's the error of the model. Now, if all those dots are, now we're talking about train valid test, and all those dots are in just your training data. Now, another example they typically show is like a really, really squiggly line that like goes through every single dot in the, in your training data. It's super squiggly, but its error is 0. That's an overfit model, because now you go to the next window of dots, which is your validation data or your training data, your test data. Those dots are not exactly the same because it's different data. So you're a little squiggly, your super squiggly f of x is gonna miss out on more dots. That's overfitting. Okay, when they're, and then when they're, yeah.
You want to do questions at the end?
Yeah, I realize this is going down like a rabbit hole. Okay, over here, I'll take one more.
Is the misspellings.
So curiously, these large language models are really good at just not caring about misspellings. And part of it has to do with the definition of a token. So the models are trained on tokens, which are typically like 3 to 4 characters, not whole words. And so for that reason, they tend to be pretty, spelling resistant, misspelling resistant. All right, so we talked about embedding, how to pick an embedding model. You've got some challenges to think about there. We talked about the indexing, which is the data structure. You've got some things to think about there, lots of choices. HNSW is a go-to if you just need something to try out at the beginning. The next thing you've got to think about is chunking. And chunking has kind of become an art form in generative AI. So it starts out with, what does your data look like? So there's like, maybe it's chat data, or maybe it's like document data, or maybe it's like Q&A data. And each one is probably going to have a different strategy to get the most out of it. So if you've got conversation data, for sure, you want to add memory to that. That's the way you're going to get the best out of that conversation data. QA pair formatting, possibly, for other data. I'm going to actually give a demo. My demo is going to be about documentation data today. So this is what I'm going to show, like a kind of an intuition about how people think about chunking that. So chunking is where, because you can't take all the data and stuff it into the embedding model, or maybe you can, well, maybe I should show this paper now. There's a couple of famous papers that came out. One is called Lost in the Middle, that showed that your accuracy does not increase with increased context length. In fact, it actually goes down. So if you're searching for, you have a question and you feed, depending on your question, but you feed it a couple sentences, or you feed it a paragraph, or you feed it like the whole Bible, its chance of being able to find the exact piece of data to answer your question kind of goes down, actually, the more stuff you feed into that. And that's called lost in the middle. That paper came out a couple years ago. So that this is kind of a reason why people are going to RAG, is because you do have to fetch out of your huge book the paragraphs that are best going to answer your question and just stuff those into your prompt as additional information rather than the whole book. Because the LLM it's gonna get kind of fuzzy for the LLM of what they're supposed to answer. Okay, so back to what I'm doing here. I've got technical docs. If I were to just take chunks of those technical docs, like 512 characters at a time, boom, 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 that's the naive chunk. But like if you think about an HTML doc, it's typically got a title and it's got headers. And if you can just take those titles and headers, which are pretty short text, and you juxtapose them into your chunk, or the technical jargon word these days is stuff. You stuff those things into your chunks, you actually get a lot more context. And it's kind of in the old days, there were, I'm gonna date myself, but there were like memory models that were trying to get longer memories. In a way, this is a cheat for that, because by stuffing the titles and the headers into your chunks, you're giving that a little bit of a cheat in terms of memory of what this little chunk of text is about. So this little first chunk of text is going to be about the Tesla Roadster, the year 2018. And then the second chunk is going to be about the Tesla Roadster, the year 2023. I had Hyundai there before, but people thought that wasn't very exciting, so I changed it to Tesla. Okay, and so now, there are two pretty common libraries out there, LangChain and Llama Index. A bunch of libraries that are convenient for doing this kind of work. They both have libraries built in that take care of this because it's a pretty well-known pattern. So in my code that I'm going to show later, I'm going to use the HTML header text splitter, which is a library that actually does this for you. Okay, I don't need to show my code because I'm going to show it later. Okay, yeah, this is the lost in the middle paper. If you go there, you're going to see a chart like this. You've got the accuracy, and you've got like first through the 20th documents. So like big picture, the accuracy goes down the more stuff you have. Now, there's a curious phenomenon, which is nicknamed needle in a haystack, which is that you'll notice that the first position and the last position have a little bit of a rise in accuracy. And it's what's come out is that, okay, the more stuff you have, the less accurate your model's going to be, but also the positioning matters. Like if it's the first or the end, if it's the beginning or the end, the model downstream is going to have a better chance of picking out the right context. So if the answer to your question is in the middle of a really long thing that you retrieved, you're kind of hosed for accuracy. You're probably not going to be able to find it. So yeah, what's his name? So yeah, we had a LangChain speaker at one of the events I organized, and this is his slide. So he showed that he did a whole bunch of experiments and research, and this was his needle in a haystack chart showing that you put like some word that you're searching for in a long context, and so the y-axis is like where you put this little thing in all the words, and then the x-axis is how big your context was. And so the interesting thing is that if your context is short, you're going to find all of those things. You can find all those little hidden gems in your text, these needles, as they're called. As your context gets bigger, you're probably going to miss more of them. Yeah. But yeah. So anyways, so yeah, there's just, those are the kind of like couple big things going on, is that the lost in the middle thing. So you don't necessarily get better results by stuffing more data into the prompt. And you also might need to watch out for the positioning of those things in your prompt. So what I think some people do is if they're going to retrieve top 10, for example, you might order them so that number 1 goes in the top position, number 2 actually goes in the bottom position, and keep on iterating like that, so that you've got all of your top content in the beginning or end of the thing you stuff in to your prompt. Okay, somebody asked a question about but I'm used to keyword search. So yeah, there are cases where keyword search really is the best thing, like some really specific word you're looking for, and you want to make sure you get exactly that word. Old-fashioned keyword search then is going to get you the answer. You don't want a semantic search. But what if you could get the best of both worlds? And this is what in vector search is called hybrid search. And actually, something that's interesting is that keyword searching is going the way of, because keywords are represented as sparse vectors, they're all vector search. It's kind of moving to the direction that all search is vector search, and keyword search is a subset or special case of vector search. But yeah, so you can take a sparse model and embedding model like BM25 or Splade seem to be pretty well known these days. And that becomes a big vector, mostly zeros. And then you have your dense vector, which I talked about in the beginning, which is the output of an encoder model. And then you do a linear combination, or you do something called a reranker. And I'll have a slide on that next. There's a whole bunch of different kind of rerankers these days. And you take like out of the top 10, then top 5, you pick your overall top 5, and you stuff that into your new improved context. And then you should be, in theory, you should get a better response. Yeah.
You find like moving the top zoom thing, it's hard to see your side. You look at the screen. Yeah.
Okay. Can I get rid of that?
I think that's good enough.
Get this better. Yeah, got it. Okay.
If you're saying that the similarity metric in the top 10 and top 5, or the sparse and the dense, is comparable, so you'd be able to take the similarities in the top 10, the similarities in the top 5, and take the top 5 of those?
Yeah, so that's the idea behind a reranker. The reranker says, okay, so you've got two lists, and like it's really the simplest one, which is what most vector databases support. It's called just a linear combination. You just take like alpha of one and 1 minus alpha of the other as a weighted combination of the two results. There's something called RRF, re-ranking something, which is also very simple. It's just taking the ranks of each list and then combining them so that you get an overall, just in case like the same result appears twice in each list, once in each list, then you get an overall ranking that represents the ranking of both lists. And then nowadays there's a neural re-ranker, which I'll talk about next. Yeah, but that's the high level idea. Yeah.
That theory is exactly what's happening here. Because of the fact that you have at the beginning, that means there's basically no context associated with the word as you wind up doing the scanning from left to right and creating the embedding. So as a result, in essence, it's usually going to have a header that is context free. That allows you to go on and take the vector, which is inside the vector space, and weight it with the keyword concepts that you have at the beginning. That potentially is happening.
They're actually totally different models that are being used for the sparse, to create the sparse vector and the dense vector. But maybe, I don't know. I'm going to show you, there's like recently, like in the last month, there's a new embedding model that's called the M3, which supposedly takes care of all vectors. So we'll see. Maybe they use that inside. And then I also want to mention for our product that there's an addition thing like metadata filtering, which is people who are used to SQL are used to like saying where such and such equals such and such. You can do that also in a vector database because you've got those extra columns and you can just do where the year is greater than 2020 for movies to recommend to me or some such thing. And we implement that as a one-step hash in the same time as you're doing the vector search. Okay, question? Yeah, I see one.
Qualifying questions. So the way I understand the site is that split the text into chunks that will deliver nothing. And for each one of them, the target context will represent.
Yes.
My question is like, what does the vector represent exactly? Is like the last token that's chunk or like the middle of it? Because as I understand, embeddings are calculated with the vector.
Yeah, so the tokens are kind of gone at this point in time. So the question is, okay, the question was, okay, sorry, can you repeat your question?
So maybe that's just my misunderstanding how it works at all. But as far as I understand, we calculate embeddings like those individual vectors on token level. So in the chunk, you will have a lot of tokens. And so then my question is, since you have only one embedding, one vector representing that chunk, what each token does it represent?
Okay, yeah. So at this point, the tokens are kind of gone because there's a level of it's called the foundational model. The foundational model was trained with tokens, sequences of tokens. But then, just like when you train a machine learning model, after you trained it, then you go to the inference phase where you just give it an input and an output comes out of the trained model. And that's what's going on here with the embeddings. So that foundational model was trained to produce a vector output given any input. You give it any input, it's going to come out with an output as in inference mode. So the individual tokens now, they were important in the training data, but they're not so much important right now in your inference. What you're going to do is you're just going to get that model has learned from lots and lots of information. We've given it like all the internet data, all kinds of books, all kinds of things to learn about. And it's learned how to represent all of that knowledge into a vector space of 768 numbers or 1536 numbers or even 256 numbers. It's learned how to represent that. So you can give it now in inference mode any sentence that, and it's gonna like, you know, with all its neural network weights, come out with a number.
Please don't do it like this.
Yeah. So like in the transformer, original transformer, okay, sorry, I have to repeat your question. So your question was, sorry again?
So I think I was just repeating what you said to make sure I understand. So you have a chunk of text now, and you don't go through attention or anything like this. Instead, you feed it directly to a new neural net that you trained to be vectors for this thing.
Correct. So the question was, so now you've got your text and you're just feeding it to a neural network to get the output. And that's what's happening. Yeah. And now that you can think of it like that neural network is fixed now. It's not going to change anymore because now you're just doing inference. Yeah.
So if you take a text document, a vector represents a page or like?
Yeah, so a vector can represent as much up to the context limit of that model. You can't fit any more into it than it allows, but up to that, it could be one character. It could be up to, you know, typically like, I think 8,000 characters these days. The same thing's going to come out, a 256 dimensional vector. Oh, one more question.
Because from the previous slide, it looks like you actually want smaller chunks, like you want like 1,000 tokens or something like this, because otherwise you were like not finding the accuracy was going down.
Yeah.
But then it looks like everyone like is in this race to get better and bigger tokens. So do you have any guess why?
Okay, so the question was, I showed that you can get just as good accuracy, retrieval accuracy with lower dimensional embeddings. But then why is there such buzz about longer context these days? I think it's because we're talking about different types of models. We're talking about the encoder model or the embedding model for the smaller context gives just as good accuracy. And then the LLM is the generator model, the GPT part of generation. And those, that's where your people are trying to get longer and longer context, because sometimes the question people want to ask is, hey, take this huge thing, and it might be like 100 pages of like the latest legislation about AI. Feed this, why don't you give me a 5-sentence summary of all this gobbledygook stuff? And you want a really long context window for that. So it is useful sometimes to have that. Okay. Okay, a little bit about rebankers. This is going to be just kind of just so you're aware. I don't expect anybody to become super. Yeah. Well, I think it's interesting anyway. So because there seems to be a lot of buzz around rebankers in the world of RAG. So when you're doing a straight up cosine similarity search, they call it a no interaction. There's no extra post processing or anything that goes on about combining vectors. BERT, which is what most of the embedding models are based on, the sentence transformer model, it is classified in the rebanking world as an early interaction model because the relationships between your questions and your docs are calculated as part of the training of that model. So that's called early interaction. Now, late interaction is this thing called a cross encoder, which people thought they had to do for a long time. And cross encoders are calculated after you've done your search and you have your vectors. And like maybe you have your sparse vector and you have your dense vector and you want to combine them. Cross encoding called late interaction because your vectors already exist. Now you're just trying to find the best of both worlds out of all those vectors. The problem is that I mean, it was kind of a simple mistake, is that people were trying to do this calculation on the fly, and it really slows down your chatbot if you have to additionally do this cross-encoding step to rebank. With a slight twist, and okay, more than a slight twist, what's come out is these things called Colbert late interaction rebankers, and they're neural rebankers that are pre-calculated actually. So they're also taken after you've done both of your vector searches, your sparse and your dense, for example, and now you combine them, but you do them with a neural model itself, and then you do this offline ahead of time, and that way when you're querying again, it becomes just an inference to do the rebanking instead of on the fly calculation. So I've got links to these papers. The Colbert V2, for example, is one of the most cited papers in the last year. I was really shocked. So people were really crazy about this Colbert rebanker thing. So basically it's taking it's like taking all the possible questions and all the possible outputs and calculating pre-calculating weights so that they can be stored separately. Here's another view. Another one of my speakers gave me this slide. So you think of it like you're doing your query and you get either a dense vector or a sparse vector, depending on if you're doing semantic search or keyword search. Then that's stage 1, and you get your search results. Then you apply the rebanker, which is a late interaction rebanker, as stage 2, and then you get your overall rebank documents. Yeah.
Corbin, do you also do the node parser where you add the header? Does that
So that would be inside whether you're doing those, that would be, for example, inside the vector search. Yeah.
Both of them actually build a better context.
Well, so the rebanker is now disjoint from however you did your vector search. So you do your vector search however you want, you get your 2 vectors. The rebanker's job is just to combine those vectors in the most optimal way. Yeah, so all this stuff about the rebanker though, the bottom line is, it's not going to be a huge gain. So I know it's very exciting, but we're talking about like a 2%, a 1 to 2% accuracy improvement here. So in the paper themselves, they talk about performance using the Miracle multilingual data set, using NDCG 10, which is a measure of top K equals 10 rankings compared to the true rankings that should have come out. That's what this NDCG at 10 means. And you'll see here between taking just the dense vector, just the sparse vector, multi-vector means you can combine maybe multiple dense vectors. Dense and sparse means you've combined a dense vector with a sparse vector. And then all means you're combining all three types of vectors, dense, sparse, and multi-dense. And you'll see here, these numbers really aren't that much bigger. So it's a lot of, I don't know, just FYI. It's cool and all, but don't expect a silver bullet here. But anyways, we added support for this hybrid search in Milvus 2.4, which just came out.
What is the full form of BG?
What's the full form of what?
Right, BG.
Oh, yes, I'm going to talk about that, embedding. So this is a new embedding model that came out in the last month, and it produces sparse vectors, dense vectors, and Colbert re-rankers all in one model. So that's why they call it the M3, because it's one model that can do three things.
Final score, so I get you would like retrieve 1,000 candidates using embedding, and then I guess normally you would want to filter those using a re-rank and get maybe 5.
Yeah.
And get to the LLM. But I don't see any mention of like how many of you checked for the final score.
Oh, 10. That's what the at 10 means.
Yeah.
Yeah.
And is there any information on like how to tune those two parameters, number of embeddings versus the number of?
Yeah, so in this case, it's not a linear combination with an alpha 1 minus alpha. It's an actual full neural network in itself. Yeah, actually, so this Miracle data set had 18 different languages, and I just didn't print them all. So yeah, English, Spanish, I don't know what these are. Yeah, 18 different languages. It's a benchmark data set. And I need to get the latest one of these. So there's another benchmark, which is, remember we talked about, we've been talking about embedding models a lot. There's the other side is the generator. And the generator is a whole bunch, these are probably the more famous of the models. So things like GPT, GPT 3.5, Turbo, GPT 4, Claude 3, and 2 weeks ago, or was it just last week, Llama 3. I think, yeah, so these things are changing all the time. So you just go to these leaderboards, and this is actually one leaderboard that the industry does trust, the LMSys leaderboard, and that's because the training data is not public. It is closely guarded for these results. So here you'll see, I think I printed this out a couple weeks ago, and I just did a search while I was waiting here to see if I could find an updated one showing Llama 3. I'm pretty sure Llama 3 is up there, because what it's trying to show is that down below here are the open source models, and up above the blue area are the closed source models. And it was for a long time that the closed source models had the highest accuracy, but what these charts are trying to show is that those open source models are catching up to the accuracy of the closed source models. And I think Llama 3 came really, really close. In my experience on my laptop, I love Llama 3. I'm actually getting great results from Llama 3, even better than GPT 3.5. The question is Llama 3 better than some of these other models? yeah, this is the thing that's coming out, is that the gap is decreasing between open source and closed source, and it's probably gonna get smaller and smaller. Maybe even open source will surpass closed source at some point, which I think as developers, everybody's hoping. Because that means those weights are open and you can fiddle with them and you can do all kinds of stuff and have fun with them if they're open. And also you can just run these models for free, which is when I'm creating demos, I really appreciate, because I don't want to rack up a big bill just creating a demo. Yeah.
It looks like flow on the left hand side. Or if there's a transform, the function.
Probably. Oh, I did accidentally cut off some of this chart. Oh, there's GPT-4. So GPT-4 came out in January.
There's one.
Oh,
Working on March 14th to go.
23.
I didn't put that.
Oh, there's a GPT-4.
Yeah.
Maybe they left some of the digits off because some, there's like the 1106 and 0325 and all these extra names to the models.
Also like berries. Last winter.
Yeah. So then they retrained it. And then also I realized after the most recent OpenAI announcement that they changed it so that instead of saying 11 or whatever model I was using, 0225 or whatever, that now they changed their policy that now you use the pinned model, GPT 3.5 Turbo, and it's automatically going to use the cheapest model they just most recently released. So you just kind of have to keep an eye on this API stuff and the naming conventions. So yeah, I changed all my code to that because of the announcement. But yeah, this is just meant to be like a high level. If you go to the actual leaderboard itself, it's going to be tables of numbers, and various people go out there, and I just picked one of these charts off where they plotted it to help people eyeball this closing gap between open and closed. Okay. Yeah, so anyways, a couple weeks ago, I went to a hackathon and I got some free credits. So I'm going to demo the Claude 3 Anthropic models. And then last week I downloaded the Llama 3. So I can demo both the latest two open source, or not quite open source for Claude 3. So whenever you use a closed source model, you always want to check the price page. So for example, here you can see the price of GPT 3.5 Turbo. Okay, see it was 025 was the most recent one, but now you're supposed to use the pinned version without the date, and it'll automatically use whatever the latest model is that comes out. But its price is 50 cents per input, and yeah, 50 for the input, 150 for the outputs. And then if you look at Anthropic's Claude 3, they come in 3 different flavors. Haiku is the cheapest. So it's actually cheaper than GPT 3.5 Turbo because it's going to be 25 cents for the input and $1.25 for the output. But then these are super expensive. And this is why I saved my output. I'm not going to run these today because the Opus is like $15 for the input. And per million tokens, but they're the same scale. So you're paying a lot more. And for creating demos, I love you guys, but I'm not going to spend a lot of money for my demos. Yeah.
My understanding, the product sits outside of any of these LLMs, if you just demo with Llama 3 going forward, how does it matter to you after that? I mean, why are you worried about?
This is why I like open source, because Llama 3 is free. If all these other things are not free.
No, but what I meant is that when you're demoing to people your product, Milvus and this,
Yeah.
it doesn't really matter like what the other side is. Right? I'm just
Well,
I understand.
Okay, you're saying, well, we're just a vector database. We're just sitting at this low level of the AI, generative AI infrastructure. Why do I care about showing different models? It's
What I meant is that it doesn't like from the end customer perspective, it's going to the LLM and making a round trip later on, right? Your product really doesn't care about it.
yeah, and then that is the thing that our company kind of says. We're like the shovel in the gold rush. We're just this. The question is, why should I be caring to show different LLMs in my demos? When it's a vector database, it's not part of our product, but the vector database is part of the generative AI workflow, and so that's why people sometimes just like to see, I can easily plug in different outputs, and the output is kind of related because the output is based on the input that you give it, and that input comes from the retrieval of the vector database.
So that's the Q&A part of it where you send it, get the answers, then patch it up. And
Yeah. Yeah.
Okay.
I want to put a little bit of perspective on the prices. I use GPT-4 in the API in my work, and I'll be working on it all day long, where I'm sending 20,000 tokens back and forth with typical questions that I'm testing on, and I'll be developing my application all day, and it's an unusual day that I racked up more than $1 of OpenAI charges. I think the record I ever racked up, this is just me working and developing, was $10 in a day. And that is nothing compared to my time, right? So now it's a different thing, when you start thinking about deploying your app and having thousands of users using it. But when you're developing, the price is absolutely negligible. I mean, so it's
also, developing it too, but once you want to start evaluating the framework, you're testing it, and you want to run those all over and over.
Yeah.
After it starts accruing in before you get the customer.
Yeah. And I've used it for doing the chunking as well. I feed in the documents and I take out, divide this document up into concepts, and those are my chunks. And so I go through a lot of text that way, but still my charges from OpenAI are just negligible, so, and I'm using it like continuously, for myself. So, so I don't know. I am worried about deployment, lots and lots. Yeah, it depends on your development cycle too, and how big you test with each time. I mean, ourselves, we're having like $20,000 monthly bills, OpenAI bills, because some of our developers were just doing a whole bunch of stuff. And once they get into automation, and it can rack up. Not so much actually with this kind of stuff, but there's different APIs with OpenAI, like they have this assistant where we were testing OpenAI RAG versus our RAG, and those prices were a lot higher. And so that's how we got a really big bill. Anyways, everybody agrees that open models are really nice if they're accurate. Yeah, one more question. And yeah, I'm not going to cover it too much today. Basically, you go to the OpenAI webpage, and let's see if I have it. Yeah. Yeah, so I did another talk there where I used okay, I can't really get, so yeah, you go to the playground and then you go to the assistant and you can do RAG that way. And I was just testing it. And the thing that got me was when I looked at the pricing, they charge you, so you have to upload your data to OpenAI in that case, if you're doing it this playground way, and they charge you, I don't know, per minute or what, that of the time that they hold your data. And that's, for me, that was the biggest charge.
And if I do it with myself, RAG with my own data, I mean, I can access my own data for free as much as I want. And I don't have to worry about how long I've got it there in my vector database. So that for me was kind of a gotcha. Besides, I got more accuracy from my own RAG. Okay, now I've got this thing in my way again. All right, I need to keep moving because otherwise I won't be able to show my demo. Oops. Anyways, oh. Okay, I think that's pretty much just a quick little thing about evaluation. So here's another big concept that has come about recently with generative AI is this idea called LLM as a judge. And this came about, there's a pretty famous paper, Jan Stoika from UC Berkeley Rise Lab wrote this paper where they did research and they found that using GPT-4 as a judge was just as good as a human. And the reasoning for this is that if you have a bunch of questions with ground truth answers and you ask humans to judge between possible answers, the humans will match will find that actual ground truth answer amongst all the multiple answers, like maybe 70% of the time. So humans are fallible. Humans are not always finding the right answers themselves. And you take GPT-4 and it found the right answer about the same amount of time. So the fact that humans only agree with each other, less than 100% of the time, about 70% of the time, and GPT-4 agrees about 70% of the time. Ergo, therefore, the paper says, LLM, especially GPT-4, can be used as a judge, replacing a human for the most part. And it may sound weird to say, hey, I'm going to use an LLM to judge other LLMs for the quality. But actually, right now, if you do a bunch of experiments, you're going to get about the same measurement using, especially GPT-4 at the time, you're going to get about the same quality of measurements as if you used a real human being. So this is the LLM as a judge. And it's had a big implication in terms of testing because it used to be that testing was really hard. You'd have to have a bunch of human labelers and they'd have to, you'd have to pay all these what was it called, Mechanical Turk, and you'd have to outsource people to human label a bunch of data, and then you could use this to gather evaluations. Now, because you can use LLM as a judge, you can get by with a lot smaller labeled data, like in the 20s of questions to be able to measure accurately whether your GenAI workflow, the quality of your GenAI workflow. So there's a bunch of different tools out there. Just like vector databases is a crowded space right now. The space of generative AI evaluations is also crowded. I was using this one, it's called Ragas. It's an open source RAG evaluation tool. And the theory behind it is it's using LLM as a judge, and you're measuring your system as a whole as well as each component. So your component of RAG, you can think of it like a little parallelogram. There's 4 corners of it. You've got the question that the user's asking. You're going to have the contexts that are retrieved from the vector database that match that question. You're going to have the LLM's generated response after you stuff the context and the question into the prompt. And then you're going to have a ground truth answer. And here's where, because we're using LLM as a judge, we don't need thousands of examples and labeled data examples anymore. We can get by with 20. And then you calculate all these different metrics, like was the context, was it covering the facts that the query asked for? Was it, I think I have it reversed. Was it the coverage is the recall, the precision is how many of the facts in the context were correct. Faithfulness, how much did the answer correspond, not veer too far from the context, and, how about the answer? So I'm kind of running out of time, so I'll just leave you with there's a paper about this, there's a GitHub, and I'm going to move to my demo. Okay. All right. I probably need to make this bigger. Yeah. So I'm going to kind of do this demo really fast. Yeah, so just normal imports. I'm gonna take my Milvus technical docs and download them. I already downloaded them and saved them in a local directory. So now all I do is I import my LangChain and I all I have to do is load them from directory. And I'm gonna end up with 22 documents. So 22 HTML files represent all of our technical docs. Now I can start up Milvus. I'm going to run it from a local Docker in this case. You could run it from free tier as well. Sometimes I demo that. But right now I'm just going to run it from a local Docker. Make this small. Okay, so I just printed out so it's the most recent release of a release candidate that I'm using for my server. I'm not going to use this cloud this time. Okay, now you need to choose an embedding model. So you saw that there's all kinds of embedding models you can choose. I'm going to choose that latest and greatest BGE M3, which can produce it's 100 different languages, dense or sparse or multi-vector retrievals, and Colbert re-rankers. So I'm going to go for the latest and greatest. We have built-in support for that in Milvus, so it's kind of nice. All I have to do is just import it, import the checkpoint, and then I can just use it right away. And I just, out of convenience, print out what are the dimensions. So you can see the dense dimension is 1024. The sparse is really big because it's mostly zeros, and the Colbert dim is 1024. Okay, so now I'm going to create a collection. A collection in vector databases, you can think of it like a table. So I now also decide to use HNSW in this case. So here, because I'm going to use both sparse and dense, I just spell them out in the schema directly that I'm using sparse and dense. And I declare my HNSW hyperparameters, and there I've dropped and created a brand new collection. Okay, now the chunking step. So I'm going to demonstrate two chunkings. One is a simple chunking, where I just chunk with a fixed length of 512 characters with a 10% overlap. And when I run this cell, I'm going to end up converting my 22 original documents into 362 chunks. I can also do this fancier chunking, where I use the structure of the HTML to inject the headers into the chunks to give it a little bit longer context understanding. And you can tell it's different because my 22 chunks in that case turned into a different number of chunks. So it did do something different. And as expected, fewer chunks. I also typically like to just double check here that sources, because I'm gonna need my grounding sources and make sure that those are indeed going to websites that work. But the Wi-Fi is really slow here. Okay. Then, okay, now I'm just gonna, for convenience, they're expecting it to be in a list of strings. I'm just gonna move it to that list of strings format and insert this into the vector database. So when you insert it, you're gonna insert things that it consists of the chunk, which is the original text, the HTML headers, the source where that came from, because I'm going to want to cite that source later. And then I'm going to have two vectors, a dense vector and a sparse vector. And I'm going to insert those tuples into the vector database. So that's pretty much what I've got. It's a chunk list of these, a list of dictionaries. I call them chunk list, and I inserted those. Wait, I just created that, and then I do the insert. Okay, so So now I've got my things all my vectors in the database, 304 vectors, so it's a really small example here. I'm just gonna show like this little cell because people ask me a lot of times about some API calls. So you can do API calls on your vector database to just like double check, okay, how many rows do you have? Tell me about my collection. It'll give you all kinds of stuff in the describe about your collection. So that's convenient to know about. Okay, so now we're ready to ask a question. So I'm gonna ask, I have 4 different questions here that I could ask. I'm gonna ask, what do the parameters for HNSW mean? So now I'm ready to do the vector search. So what you're doing is, you see here again, I do the embedding of my question, using the same model, and then I'm going to use my HNSW parameters to search. And in this case, I did a top k equals 2. I didn't have time to talk too much about that, but basically the distribution of your distances is going to vary. So like in my case, I like to matplotlib a whole bunch of distances, and I can see that in my case, top k is 2 is good enough, is pretty good. It catches the highest distances, and then there's a drop off of distances in my particular distribution. So yeah, so I retrieve top k is 2. I'm gonna just assemble those results into, for convenience, into a zipped list of contexts and distances and sources and metadatas. And then here I was just printing out the difference between when I did the re-ranking or not. So here in this search statement, you can see I can either search with re-rank equals a re-ranker, or re-rank with a like 50-50, which means no re-ranking. So, and what I found was kind of jives with the research is that if I plot out the difference between when I have re-rank is true and when I have re-rank is false, they're exactly the same except for like the 7th to 10th positions. And that's not really going to affect for my application, that's not going to affect my answer, because those, like, when you get down that far, those were like really like far away vectors anyways, and they weren't so good for my context anyways, because I'm only keeping the top 2. So in this case, re-ranking would be the same as without. Okay, so I'm going to keep my top 2. I guess I just printed that out just to make sure it looks good. Okay, now I'm ready to generate chat. So I'm going to take my contexts, put them all together into a join, set my temperature. So with LLMs, you always want to think about temperature. Lower temperatures means it's going to be more factual, and they say higher temperatures means it's more creative. It takes a little bit more liberty. Give it a random seed so it's reproducible. Okay, so if you haven't heard of Ollama, this is another new thing that I highly recommend to check out. It was super easy. You just go to the website and you can download it. And what they've done is they've taken these any open source LLM, they've taken and optimized them for CPU. And so this is the way that I can run on my dinky little laptop. I can run Llama 3 because I'm taking the format, which is GGUF, which is the CPU optimized format. And in addition, they've done quantizations. And if you're curious, I have a link here to look up what these quantization codes mean, but you can think of quantization as a compression of a vector. And so the combination of the optimization for CPU and the compression means I can run this through Ollama on my laptop. So that's what I'm doing here. So I just for, just to make sure that I understand what I've got here, I print out the model parameters that I can see. Its format is GGUF. Its parameter size is 8 billion. So it's a smaller Llama 3 instruct, and its quantization level is 4, Q4, which is the highest quantization, which, Ollama will automatically download the best model for your compute. And in my case, I've got the dinkiest laptop, so they had to have the highest compression level. When you get to Q8, you may as well, you don't need any compression because basically you've got a pretty big compute. So yeah, here's my system prompt. Just, it says, given the provided context, your task is to understand the content and accurately answer the question based on the information provided. Then I feed it the context and I feed it the sources. Submit it to Llama 3 via Ollama, and it's running locally, so it's gonna take a little while. I don't have a big computer. All right, and then I come up with an answer, and eyeballing it, it looks pretty good because it's got the 3 parameters. It's got M, it's got EF, which is done during search, and it's got EF. Oops, I do see an error here. There should be 3 parameters, and it's repeated twice. One should be EF construction during index building and EF during search. So it's slightly off. Okay, now I'm not gonna actually run Anthropic because I told you it costs too much for me. I saved the screen grab when I ran it. I can run OpenAI. It's not that expensive.
How would you add, like, you've got the same mistake, do you think?
Suppose I had run it. So because I set a seed this time, I might not have had the seed when I ran it before. Nope, here it is. See, I had that same error the last time I ran it. So the seed worked. All right, so now I'm gonna run OpenAI. Okay, and I got a good answer. I see M, EF construction, and EF. So heuristically, intuitively, I think I should get a better Ragas score for OpenAI. So with OpenAI, eyeballing this answer, it looks better to me as a human. Because the next I'm going to show how to evaluate. So I'm going to take import all of those Ragas metrics. And this is my little ground truth data. So I only had 4 questions. I'm going to take, and I'm going to say I want to evaluate the answers, I guess. Oops, should have changed it to Llama just to see that. .557. Okay, I got 0.58 last time. So there, I do need to maybe talk to those developers about where to set my random seed for my LLM as critic, because there should be a way to reproduce their metrics as well, instead of having slightly different metrics. But
OpenAI random seed.
so yeah, in the ballpark, this is what I calculated before was 0.58. I just now calculated 0.55. But here's my punchline is I ran Ragas on all of my combinations of different contexts, the simple context versus the HTML splitter, and I got a higher retrieval score, which is what you'd expect. And it's actually, this was surprised me. It was 68% better, which is a much better score than I thought it would be. And I also ran fixing the chunking strategy. Then I varied the LLM, and I saw that maybe I changed something. But I think what I got was not that much of an improvement by changing the LLM. Oh yeah, so Llama 3 was pretty good actually compared to the GPT 3.5 Turbo. In this case, it's actually kind of reversed, so maybe I made a mistake, but they're pretty close to each other. Yeah, so that's kind of RAG in a box, and I hopefully elucidated some of the decision points and things you need to think about when you're creating your own pipelines and things that you need to decide. So thank you. All right. You're a great, very curious audience, so thank you.
I'd like to ask, how many people feel like they got them down the talk? How many people they learned something tonight?
It was one of the best topics of the book.
Yeah.
Oh, wow. Thank you so much. Thank you. All right.